Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
It really is a pleasure to be here.
This is Andrew and Renee. Welcome to the Stacks series.
And today we have, well, it's quite an expedition we're about to embark on. We're going to be traversing time, soil, and the very DNA of our food systems.
That's a great way to put it. Today we are exploring the nexus of paleoclimatology and agronomic evolution.
All right.
And more specifically, we are looking at how reconstructing ancient environmental records can inform modern agricultural resilience.
Right. Which is, a very academic way of saying something really fundamental. We are going to look at how people farmed 5,000 years ago to try and figure out how we're going to eat 5 years from now.
Exactly. And I think it's important to set the stage here because the stakes are, well, they're incredibly high. We're living in this moment where the phrase climate crisis isn't just a headline anymore.
No, it's not.
It's the background noise of our daily lives. We are looking at food security challenges right now in the mid-2020s that are genuinely scary. You've got shifting rain patterns, you have soil degradation, you have these temperature spikes that can literally cook crops in the field.
It's the volatility. I think that's the key word that hangs over everything. It's the unpredictability. And, usually when we face these huge modern problems, our reflex is to look for hyper-modern solutions.
Of course, we want the newest app.
We want the app, we want the newest genetically modified super seed or, some high-tech vertical farming tower in the middle of a city. We think technology is the only way forward.
We look forward. We always look forward. We want that sci-fi fix. But the hook for today's whole discussion is that we're going to be doing the exact opposite. We're looking backward.
And not just a little bit backward?
No, I don't mean to the Green Revolution of the 1960s. I mean way back. We're talking about the Neolithic. We're talking about the Incas.
We're looking for the forgotten strategies. And I think our core mission today is to really understand how ancient civilizations adapted to massive climate shifts because, contrary to what a lot of people think, they absolutely did face them and how their farming strategies might actually hold a key to surviving our own future.
It feels almost like we're trying to find an instruction manual that we threw in the trash a few millennia ago because we thought we knew better.
That is a very fair assessment. I think we can say we traded resilience for efficiency, and now we're realizing that was a very, very risky trade.
So to do that, we have a massive stack of sources today. We're covering everything from some really high-tech simulation studies of Australian soil carbon dynamics, which gets really technical and frankly surprising, all the way to archaeological reports on Inca terraces and even genetic studies of ancient wheat varieties.
Yeah, it's a real convergence of archaeology, climatology, and modern agronomy. And it's rare to see these fields talk to each other, but when they do, the results can be explosive.
Absolutely. So let's get into it. Let's start with the foundations, what we think we know.
And to do that, let's start with the weather.
Paleoclimatology.
Right.
Okay, so when we talk about the climate of, say, ancient Egypt or Mesopotamia, we obviously don't have weather station data. There were no thermometers 5,000 years ago.
No satellites, no weather balloons.
Right. So how do we actually know what the weather was like when the pharaohs were building the pyramids? Are we just guessing?
We were definitely not guessing, no. We rely on what we call proxy data, which is a simple idea, really. Since we don't have direct instrument records, we look for natural recorders of climate variability.
Okay.
You can think of these as accidental hard drives that nature just left lying around for us.
Nature's hard drive. I like that. But what does that actually look like? Are we just looking at rocks and saying, this looks like a dry rock?
It's a lot more delicate and a lot more clever than that. We are talking about evidence that's been preserved in things like fossils, in sediments at the bottom of lakes, in ice cores from glaciers, tree rings, corals, even microscopic pollen.
Okay, you have to break that down. How does a tiny piece of pollen or a layer of mud tell you if it rained a lot in 3000 BC?
We'll take diatoms, for example. These are microscopic algae. They have these beautiful little silica shells, and they're found in sediment layers in lakes or oceans. And the key thing is they are incredibly sensitive.
Sensitive how?
Different species of diatoms thrive in very, very specific conditions. Some like salty water, some only live in fresh water, some like it cold, some like it warm.
So they're picky eaters.
Extremely picky. So let's imagine you go out onto a lake and you drill a core. You pull up this long tube of mud. As you go down that tube, you are literally going back in time.
Right. The deeper you go, the older it is.
Exactly. So if you find a layer from, say, 4,000 years ago that is suddenly packed with salt-loving diatoms, but you're in what is now a freshwater lake, you know something drastic must have happened.
The lake must have dried up, become more saline, or maybe the sea level rose and flooded it.
Exactly. You can reconstruct the salinity and the temperature of that water with incredible precision. And it goes even further than that. We look at charcoal in those sediment layers.
For fires.
For fire frequency, yeah. If you see a sudden spike in charcoal, you're likely looking at a prolonged drought period where wildfires were just rampant. It's like a scar in the geological record.
So there's real detective work. You're building a crime scene photo of the climate piece by piece from all these different clues.
That's it. We check atmospheric circulation patterns from the air trapped in bubbles in ancient ice cores from Greenland. We can look at tree rings to see year-by-year rainfall. It allows us to build a surprisingly high-resolution picture of the past.
And this brings us to what's probably the most important context for agriculture, the Holocene.
Holocene, yes.
That's the geological epoch we are in right now, correct? Or at least the one we were in until we started messing things up so much.
Correct. The Holocene is the last 11,700 years, roughly since the end of the last major ice age. And in the grand scheme of Earth history, the Holocene is bizarrely unique.
Unique how? What's so special about it?
It's stable. I mean, remarkably stable. Before the Holocene, in the Pleistocene epoch, the climate was chaotic. It was just wild. Temperatures would swing dramatically, sometimes within the span of a single human lifetime. It was a roller coaster.
And the Holocene.
The Holocene was the Goldilocks era. Not too hot, not too cold, and crucially, it was predictable. The seasons came when you expected them to.
And that predictability is what allowed us to stop chasing our food and actually start growing it.
Precisely. This is the cradle of agriculture. If the climate had been swinging wildly like it did in the Pleistocene, it's highly unlikely that humans would have ever invested the incredible energy that's required to plant crops.
Because why would you? Why plant a field of wheat that takes 6 months to mature if you have no idea if a sudden ice storm or a brutal heat wave is going to hit next month and wipe it all out?
The risk would be too high. Stability reduces risk, and when risk goes down, investment in new ideas goes up.
That makes sense.
Exactly. And we see this transition so clearly in the archaeology of the Levant and northern Syria during that switch from the late Pleistocene to the early Holocene. The sources show a clear shift where wild cultivation, which is just, tending to patches of wild plants, began slowly moving toward full domestication.
And that brings us to the roots of agronomy. And, one thing that really stood out to me, the reading for this, was this idea that domestication wasn't just humans conquering nature. We have this popular narrative of man the master, taming the wild wheat. But the reality was, it was much messier.
Much, much messier. I think a better term is an ecological entanglement. We often tell the story as if humans were smart, we saw a seed, we planted it, we controlled it. But the biological evidence suggests it was a coevolution. We changed the plants, but the plants definitely changed us.
Okay, give me an example of the biology. How did we actually change the plants on a genetic level?
Well, look at the genetic changes in a crop like rice. We have phytolith evidence, and phytoliths are these tiny microscopic silica structures inside plants that fossilize really well from East China. They show us how rice evolved traits that made it completely dependent on humans. The most famous example is the non-shattering rachis.
Okay, explain that. What is a rachis and why does it shatter?
So the rachis is the little part of the stem that holds the seeds, the grains, onto the stalk. In the wild, a plant wants to spread its genes, right?
Okay.
So when the seeds are ripe, the rachis becomes brittle and it shatters, which throws the seeds onto the ground so they can grow next year. It's a dispersal mechanism.
Which is great for the plant. But if I'm a farmer trying to collect those seeds, that's a nightmare. I walk up to the plant to harvest it, and all the food just falls into the dirt.
Exactly. It's useless to you. You want the seeds to stay on the stalk until you are ready to cut it. So what happened is that early humans naturally collected the seeds from the mutant plants where the seeds stayed on the stalk simply because those were the only ones they could successfully carry home.
So they weren't even consciously selecting for it. They were just picking the ones that worked.
It was an unconscious selection process. They planted those seeds. Over generations, they accidentally selected for a genetic mutation where the plant couldn't drop its seeds anymore.
So the plant lost the ability to reproduce on its own in the wild.
Yes. Domesticated wheat or rice is basically helpless. It needs a human to come along, cut it, thresh it, and sow the seeds for next year. But here's the trap. Humans also became dependent. Once we had these reliable, high-calorie crops, our populations boomed. We couldn't go back to just hunting and gathering.
We were locked in.
We were locked into this new way of life. It became a 10,000-year marriage. And like any long marriage, you have to figure out how to make it work through the good times and the bad.
And the bad times were the climate fluctuations. Because even in the stable Holocene, there were still droughts and floods and bad years.
Exactly. So civilizations had to figure out how to create their own stability where nature didn't provide it. And this is where we see these incredible ancient systems of stability emerging all over the world.
Let's tour a few of these because I think, when we think of ancient farming, we tend to think primitive. But some of these systems were just mind-bogglingly sophisticated. Let's start with a classic, Egypt and the Nile.
The classic example, yes, this was basin irrigation. Now think about how we irrigate today. We drill a well, we have a big pump, we use a lot of energy to pull water out of the ground, and we spray it on the field when the plant looks thirsty.
Right. It's a very active, very energy-intensive process.
And we force the water to go where we want it to go.
You force it to the plant.
The Egyptians did something completely different. They practiced flood recession agriculture. They worked with the natural rhythm of the river, not against it. They knew the Nile would flood every single year, like clockwork.
And the flood didn't just bring water.
No, this is the crucial part. It brought nutrient-rich silt all the way from the Ethiopian highlands. It was a massive annual delivery of free fertilizer.
The best fertilizer in the world.
Absolutely. So what they did was build these vast networks of dikes and basins. You can think of them as huge earthen bathtubs, basically, to trap this floodwater on the land for weeks at a time. They would just let the soil soak up the moisture and, importantly, let that heavy, rich silt settle out of the water.
I mean one.
Then, when the river level naturally dropped, they would open the sluices, let the remaining water drain back into the Nile, and they would plant their seeds in this perfect, wet, black mud.
So they weren't fighting the flood at all. They were capturing it. They were harnessing its power.
Exactly. It was a regenerative cycle that was built into the very hydrology of the region, and it's why they could farm that same land for thousands of years without depleting the soil because the river renewed it for free every single year.
Okay, now let's contrast that with the Andes, with the Incas. This is a completely different environment. We're talking vertical, rocky, high altitude. You can't depend on a nice, gentle, predictable flood there.
No, not at all. The Andes are a nightmare for modern industrial farming. You can't drive a tractor up a 45-degree slope. It's just not possible. But the Incas mastered it.
They use terracing, of course.
Yeah.
We've all seen the pictures of those beautiful steps carved into the mountainside.
Right, the terraces. And yes, that creates flat land, which is the obvious benefit. But it's so much more than that. The stone walls of the terraces absorb heat from the sun during the day, and then they release that heat slowly overnight, which creates a microclimate and helps prevent frost from killing the crops. But the real genius, the part that's just breathtaking, was their water management. The Incas had a system called immunas.
This is the part that I found almost hard to believe when I was reading about it. The source described it as planting water.
It is a beautiful and a very accurate concept.
But hang on a second. I have to stop you on the planting water part, because when I first read that, I thought it had to be a translation error or maybe some kind of mystical metaphor. You build a dam to stop water. You don't build a complex system just to let it leak away into the ground. That seems completely counterproductive. Why would you want your water to just disappear into the mountain?
It does seem completely counterintuitive if you're thinking like a 21st century engineer. You're right. We want control. We want the water in a concrete tank where we can see it, measure it, and release it right now. The Incas were playing a much longer game, a time delay game.
How so? Explain that.
Think of the mountain itself as a giant rocky sponge. During the rainy season up in the highlands, you have too much water. It's a problem. If you just let it run down the mountainside, it causes landslides and floods down in the valleys. It's a disaster. So the Incas built these stone-lined canals to divert that excess water away from the streams and into very specific geological fracture zones. Basically, they found natural cracks in the rock.
So they're intentionally flooding the inside of the mountain.
They are charging the aquifer. They are forcing water deep into that sponge. And it can take weeks, sometimes months, for that water to trickle and percolate through all the rock and sand filters inside the mountain.
And that's the planting.
That's the planting. And the harvest happens 3, maybe 4 months later. Just when the dry season hits hard and the rivers are drying up, these springs lower down the mountain suddenly start bubbling with fresh, clean water. The timing is perfect. They were using the geology of the mountain itself as a slow-release reservoir.
That is just, it's incredible. But, and I have to ask the economic question here, The amount of labor required to build stone canals at 4,000 meters altitude,
Without wheels.
without large draft animals. I mean, if I'm an Inca farmer, why am I hauling heavy rocks up a mountain to plant water that I won't personally see for 3 months? What was the incentive structure for that?
The scale of the labor is staggering. And that's the catch, you're right. This kind of system only works if you have a society that is organized around communal labor mita, as they called it. It was an obligation to the state.
So you can't really do this if everyone is just looking out for their own quarterly profits.
No, it would be impossible. It was a survival imperative for the whole community. If you didn't all work together to maintain the immunas, the community would starve in the dry season. The incentive was collective survival.
So the infrastructure was social as much as it was physical.
Exactly. And they combined this amazing water system with what we call vertical ecology. They farmed at many different altitudes on the same mountain. Potatoes and quinoa way up high, maize and beans lower down.
Risk management portfolio.
It was. If a freak frost killed the high altitude crops, the low altitude crops would probably survive. You diversify your assets to minimize risk.
Which brings us to another amazing system in Mesoamerica, the Chinampas, the so-called floating gardens of the Aztec capital, Tenochtitlan.
And these were arguably some of the most productive agricultural systems ever devised by humans. In some metrics, like yield per hectare, they were better than modern intensive farming.
How did they work? Were they actually floating?
Not exactly floating, more like anchored. They would build these long rectangular islands by weaving reeds together to form a sort of basket, and then they'd scoop up the organic muck, this incredibly rich, decaying organic matter, from the lake bottom and pile it on top.
I can only imagine what that must have smelled like.
It probably smelled like life.
Yeah.
Like rich, active fermentation. But think about the mechanics of it. The roots of the plants grow right down through the muck and into the water of the canals between the islands.
So it's effectively drought-proof.
Completely. You never have to water it. And the thermal mass of the water surrounding the island created these stable microclimates that protected the crops from frost.
And they didn't just grow one thing on them. This brings us to that famous polyculture, the Three Sisters.
Polyculture, yes. Corn, beans, and squash grown together. This is the absolute antithesis of modern monoculture, of 1,000 acres of nothing but corn.
But how does that work biologically? I mean, if I plant 3 different things in one pot at home, they usually just fight each other for space and light.
They do, unless they have different jobs. This is a support system. It's a team. The corn provides a tall, strong stalk for structure.
Okay.
The beans are climbers. They need something to grow up on, so they use the corn stalk as a natural trellis to get up to the sunlight. But the beans pay rent for that space.
How do beans pay rent?
They are legumes. They have a symbiotic relationship with bacteria on their roots that allows them to take nitrogen from the air, which is unusable by most plants, and fix it into the soil as a natural fertilizer for the corn and the squash.
And the squash, what's its job?
The squash grows low along the ground with these big, broad leaves. It acts as a living mulch. It shades the soil, which keeps moisture in, and suppresses the growth of weeds.
So it's a perfect roommate situation. Everyone does their part, everyone benefits.
It's a self-sustaining guild. And, nutritionally for humans, it provides a complete diet. You get your carbohydrates from the corn, your protein from the beans, and vitamins from the squash. It's a stark, stark contrast to 1,000 acres of just soybeans.
Okay, so that's the foundation. We have these incredible, elegant, ancient systems that worked with nature's patterns. And it's so tempting to stop right here and just say, the ancients knew best. Let's all go out and build Chinampas.
It is tempting.
But we need to move to our second section, active debate. Because science is messy, and it's not always as simple as old ways good, new ways bad.
Right. And for this, we have a source that really complicates that simple narrative. It's a simulation study that was done using the APSMM model. That's the Agricultural Production Systems Simulator. And it comes from a team in Australia. This is the Godia All study.
And this one dives deep into what you could call the soil carbon conundrum. Carbon farming is a huge buzzword right now.
Huge.
The idea is that we can change our farming practices to suck carbon out of the atmosphere and store it or sequester in the soil. And it's always presented as a win-win. You save a climate and you improve your soil health.
But this study essentially says, hold on, it depends. And it says it depends in big, bold, flashing letters.
Let's break this down because the details here really matter. They use this computer model to compare 2 very distinct Australian environments, one called Brigalow and another called Woburn.
And these are two very different worlds. Brigalow is a region with heavy clay soil and a wet subtropical climate, so hot and sticky. Woburn, on the other hand, has sandy soil and a dry Mediterranean-style climate.
Okay, so let's get to the first debate point that came out of this. The idea of geography versus management. We usually tell farmers, if you manage your land with the right practices, you can build soil carbon.
But the study found that the initial conditions, the soil carbon you start with, and more importantly, the climate, had a massive impact on the sequestration potential, often much, much more of an impact than what the farmer actually did on the land.
So you're saying you could be the best, most eco-friendly farmer in the world, but if you're in the wrong zip code, you could be fighting a losing battle.
In terms of building soil carbon, yes, that's what the simulation suggests. And you can see this really clearly in what they call the Brigalow reality check. This is the heavy clay soil in a hot, wet region.
Right.
The simulation showed that soil organic carbon, or SOC, almost always decreased over a 90-year period. It didn't matter if they used no-till practices. It didn't matter if they left all the crop stubble on the field. The carbon still went down.
Wait a minute, I thought clay was supposed to hold on to carbon really well. Isn't clay soil supposed to be sticky and protective of organic matter?
Physically it is, you're right. Clay particles can bind to organic matter and protect it, but you have to factor in the biology. Heat and moisture drive decomposition. Microbes, the bacteria and fungi in the soil, they love hot, wet conditions.
So they get more active.
They're like teenagers at an all-you-can-eat buffet. They just tear through the organic matter and respire it back into the atmosphere as CO2. The technical term is mineralization.
So the climate was essentially burning off the carbon faster than any farming practice could possibly put it back in.
That's it. It's a microbial furnace. You could dump truckloads of compost onto that field, and the climate would essentially eat it within a season or two.
That is a very sobering reality check for the whole carbon farming movement.
It is.
Now, let's talk about the second debate point, which I found just as surprising. I'm calling it the legume paradox. We just spent time praising the three sisters and how beans fix nitrogen. Legumes are supposed to be the heroes of regenerative agriculture.
And in many contexts, they absolutely are. But the simulation showed something very unexpected. In a wheat-chickpea rotation, where you alternate the crops each year, if they were also using synthetic fertilizer, the soil carbon actually decreased compared to just growing wheat back to back.
Hang on, let me get this straight. Planting chickpeas, a legume, made the soil carbon situation worse. How is that even possible?
Under those specific high-fertility conditions, yes. There are two main reasons this happens. The first is about biomass. Wheat is a grassy plant. It has a huge fibrous root system, and it leaves a lot of stubble behind after harvest. It's messy. Chickpeas, on the other hand, produce less total biomass. They're just smaller plants with smaller root systems.
Okay, so it's a volume game. Wheat just dumps more sheer bulk into the ground to begin with.
Right. Less plant matter going into the soil means less carbon input. Simple as that. But the second reason is about chemistry. Chickpea residue is very high in nitrogen. It breaks down incredibly quickly. It's like high-quality, high-energy food for soil microbes.
You're giving them a sugar rush.
It's a perfect analogy. You give them a sugar rush, they eat it up fast, and because they get so energized and their populations explode, they might even ramp up their activity and start eating some of the older, more stable carbon that was already in the soil.
That's the priming effect, right? You're accidentally stimulating the microbes to eat your carbon savings account.
Exactly. Now, the nuance here is absolutely critical. If you run the same simulation with no synthetic fertilizer, the legume phase becomes very beneficial.
Why the change?
Because without fertilizer, the wheat crop grows poorly. So the legume comes in, adds that free nitrogen to the soil, which then boosts the yield of the next wheat crop, which in turn creates more biomass and adds more carbon.
So legumes are great if you're in a low-input system, but if you're already in a high-input fertilized system, they might actually act as a carbon leak.
Precisely. It's a really complex trade-off that depends entirely on the background conditions.
Speaking of high-input systems, let's move to debate point 3, the nitrogen trade-off. This one feels like a real pick-your-poison situation.
It is the central dilemma of modern agriculture. The simulation for the Woburn site, that's the dry, sandy soil, showed that the single most effective way to increase plant biomass and therefore store soil carbon was to add a lot of nitrogen fertilizer.
All right, makes sense. You make the plants grow bigger, they leave behind bigger roots and more stubble, the soil carbon goes up. It's simple.
It seems simple, but at what cost? We know that high rates of nitrogen fertilization lead to leaching, where excess nitrates wash out of the soil and into the groundwater, which is a major pollutant.
Mhm.
And even worse, from a climate perspective, it leads to emissions of nitrous oxide, or N2O.
And nitrous oxide is a greenhouse gas that is, what, orders of magnitude worse than CO2?
It's about 300 times more potent than CO2 as a greenhouse gas over a 100-year period. So here is the insight, and it's a painful one. You might be successfully sequestering carbon in the soil, but to achieve that, you are releasing this incredibly potent nitrous oxide into the atmosphere.
So you could be winning the soil carbon battle, but actually losing the overall climate war.
That is the definition of a wicked problem. You try to fix one metric, and you end up breaking another one that's even more important. True climate mitigation requires balancing both the carbon and the nitrogen cycles. You can't just look at one in isolation.
And finally, from this study, debate point 4, tillage and stubble. We hear all the time that no-till is the holy grail of soil health. Don't plow the field, leave the soil structure alone.
Yeah, and in general, it is very good for soil structure and for water retention. I'm certainly not arguing against no-till as a practice, but what the study showed was that zero tillage and stubble retention, leaving the crop residue on the surface, had a much smaller impact on the final soil carbon levels than either the fertilization rate or the climate itself.
So it's not a magic wand that solves the problem.
It's not a silver bullet. It helps, but it's not the primary driver, at least not in these specific Australian environments. I think the big takeaway from this really deep analysis is that context is everything. You cannot just copy-paste a farming method from a temperate forest in North America to a subtropical clay plain in Australia and expect to get the same results.
So science is messy. The ancient ways were clearly brilliant, but we can't just blindly apply them everywhere. And our modern fixes like carbon farming have all these hidden costs and trade-offs.
Right.
But that doesn't mean we should just give up. It means we have to get smarter. Which leads us perfectly into our third section, frontiers. What might change everything?
This is where it gets really exciting, because this is where we start to combine that ancient wisdom with cutting-edge technology. We stop seeing them as opposites and start seeing them as partners.
Let's start with genetic resilience. We talked earlier about how we domesticated crops. But in the last 100 years or so, we've really narrowed that gene pool, haven't we?
We have. Dramatically. The Green Revolution in the mid-20th century was all about maximizing yield. We bred crops that were short so they wouldn't fall over, that stood up straight, that took synthetic fertilizer really well and produced massive amounts of calories. But in doing so, we lost a huge amount of genetic diversity. We lost the land races.
Land races. That's a term that comes up a lot in these papers. Can you define that for us?
A landrace is a domesticated, locally adapted variety of plant that has developed over a very long time. These aren't wild plants, but they also aren't modern commercial hybrids. These are the ancient wheats that were grown by farmers in small villages in Turkey or Iran for thousands of years. They evolved in the field, adapting to the local pests, the local diseases, and the local climate.
And we have a source here that discusses a study of 827 of these wheat land races.
And it's a genetic goldmine. These ancient varieties have been sitting in gene banks, some of them just gathering dust for decades. The study found that they hold genetic secrets for things like drought tolerance and heat resistance that our modern high-performance Ferrari crops have completely lost.
So the modern crop is a Ferrari. It's incredibly fast and high performance, but if the road gets bumpy or you run out of premium gas, it breaks down immediately. The landrace is what?
It's a Camel, or maybe a Land Rover from the 1970s. It's not fast, it's not flashy, but it will get you there, even if there's no road and no water.
And now we're trying to put the Camel's engine inside the Ferrari's body.
In a way, yes, a very precise way. We are using omics, genomics, metabolomics to scan the DNA of these land races and find the specific genes responsible for that toughness. They identified one in particular called TAMYB7A1.
TAMYB7-A1. Sounds very catchy, like a droid from Star Wars. What does it do?
It's a transcription factor, which means it's a master gene that controlled a bunch of other genes. In this case, it controls water use efficiency. Specifically, it helps the plant regulate its stomata, which are the tiny little pores on the leaves that the plant breathes through.
Yeah.
When it gets dry, this gene helps the plant close those pores faster and tighter to keep precious water from escaping.
So it basically teaches the plant to hold its breath during a drought.
That's a great way of putting it. So by finding this gene in the ancient wheat, scientists can now use precision breeding breeding or even gene editing tools like CRISPR to reinsert that ancient resilience back into our modern high-yield crops.
That is the absolute definition of retro-innovation, bringing the old software code back into the new operating system.
Exactly. And speaking of retro-innovation, let's look at the tech side of things. Digital twins and satellites.
We have a source here from a company called Farminaut, and they're using satellite sensors to monitor these ancient farming methods. This really seems like a clash of different eras.
It does on the surface, but it's a brilliant synthesis. Imagine using high-resolution, space-based data to check the soil organic carbon levels or the moisture retention in a 2,000-year-old terraced field in the Andes. We can create a digital twin, a perfect virtual replica of that farm inside a supercomputer, to test how those ancient terraces would perform under the climate scenarios we expect in 2050.
So we don't have to just guess if the ancient terraces will work in the future. We can measure it from orbit and then model it.
And we can optimize it. We can see exactly which part of a terrace is drying out faster than another and adjust the water flow, maybe using a small solar-powered automated sluice gate on an ancient Inca canal.
Wow, that really does bridge the gap between the stone tool and the smartphone.
It does. And there is also this fascinating movement in what's being called regenerative viticulture.
Vineyards. Usually when I see a vineyard, it's just these perfectly manicured rows of grapes and bare, often tilled earth. Maybe a rose bush at the end of the row for decoration.
Traditionally, yes, it's a classic monoculture. But this new frontier is about applying these regenerative principles. They are trying to move from being sustainable, which really just means maintaining the status quo, not making things worse, to being regenerative, which means actively improving the entire ecosystem.
So how do you do that in a vineyard?
You bring in animals, you put sheep in the vineyards.
Won't the sheep just eat all the grapes? This seems like a bad business model for a winery.
You have to time it right, of course. You bring them in during the winter or early spring before the buds break on the vines. The sheep come in and they eat the cover crops, what we would call the weeds between the rows. They trample all that biomass into the soil with their hooves, and crucially, they poop.
Free fertilizer.
Natural, microbial-rich fertilizer. It closes the loop. It cycles nutrients. It mimics those ancient mixed farming systems where animals and plants always live together. And the argument is that it turns a grape factory back into a living ecosystem. And many winemakers will tell you the wine tastes better because the soil is more alive.
And finally, under this frontier section, we have water management 2.0. We talked about those incredible Inca munas earlier.
Right. And what's happening now is that the country of Peru is currently investing in a massive irrigation boom. I think the plan is for 22 new mega projects, concrete dams, pipelines, the modern works. But at the same time, they are also looking back and investing in restoring those ancient amunas.
It's a hybrid approach. It's not one or the other.
Exactly. The concept is green infrastructure meets gray infrastructure. You use the big concrete dams, the gray, for the bulk water storage, but you also restore the high mountain wetlands and those ancient infiltration canals, the green, to slow the water down before it ever even reaches the dam.
And then presumably you layer AI-powered precision farming on top of it all to make sure you don't waste a single drop of that precious water when it finally reaches the field.
It's trying to get the best of both worlds. Ancient wisdom for collection, modern tech for distribution.
This all brings us to our final and perhaps most important section, the implications. We've covered the history, the science, the tech. But what does this all mean for society, for our economics, for our ethics?
I think the single biggest implication is this fundamental clash between two philosophies, resilience versus efficiency.
Unpack that for us.
Modern agriculture and really modern capitalism prioritizes efficiency above all else. Maximum yield per acre, uniformity of product, monoculture for ease of harvest, just-in-time delivery systems. And that works great. It works fantastically when the climate is stable and the global supply chains are smooth.
But as we established right at the beginning, that Holocene stability is ending. The supply chains are not smooth.
Exactly. So the efficient system is proving to be incredibly brittle. It's like glass. It's very strong until you hit it in just the wrong spot, and then the whole thing shatters.
So one bad heat wave, one new pest that the monoculture has no resistance to, one war in a major breadbasket region, and the whole system is at risk.
And we've seen all three of those things happen in the last few years. Ancient agriculture, on the other hand, prioritized resilience, survival through diversity, through polyculture. If the corn crop fails one year, the beans might still survive. If the valley floods, the crops on the high terraces survive. The implication for us is that we may have to accept potentially lower yields, less raw efficiency,
Hmm.
in exchange for much higher stability. It's like buying insurance. Diversity is an insurance policy.
But that's a really hard sell economically, isn't it? Imagine trying to tell a farmer or the massive agribusiness corporation, hey, we want you to grow less food and make less money this year, but don't worry, you'll be safer in the event of a 100-year flood. The market doesn't reward safety, it rewards volume and profit.
That is the core economic hurdle, which leads directly to the next implication: the human element and labor. Those ancient methods, the terraces, the chinampas, the polycultures, they are incredibly labor-intensive.
You can't drive a massive combine harvester on an Inca terrace, and you can't use a machine to pick beans if they're all wrapped around corn stalks in a mixed field.
No. And in a world of rapid urbanization where everyone is moving from the countryside to cities, who is going to do that work? It's not realistic to think we can all become subsistence farmers again. That's not a viable future for 10 billion people.
So is this all just a nice academic daydream?
I don't think so. This is where robotics has to come in. We need to develop smart tools that can navigate these complex, uneven environments. We need swarms of small, agile robots that can work a polyculture field, that can tell the difference between a ripe bean and a corn stalk.
So the robot replaces the intensive peasant labor of the past. It allows the complex ecological structure to exist without requiring 90% of the population to work in the fields to maintain it.
That's the hope. We use high-tech labor to enable what is essentially a low-tech biological system to flourish.
And there's a big ethical shift here too, isn't there? Regarding how we even think about the soil itself.
Yes, we are slowly shifting the framework from seeing soil as a substrate, which is basically just an inert sponge to hold chemical fertilizers and water, to seeing soil as a habitat.
It's alive.
It's a living entity. It's an entire ecosystem, a microbiome with billions of organisms, and there is a direct and growing line of evidence connecting soil health to human health. The nutrient density in our food comes directly from the complexity of life in the soil. We are realizing that by sterilizing our soil to chase efficiency, we have been systematically diluting the nutrition of our food for decades.
And the carbon markets are trying to monetize this idea, this concept of carbon farming.
Yes, the idea is to pay farmers not just for the food they produce, but for the ecosystem service of storing carbon. But as that Australian study so clearly warned us, measuring this is incredibly tricky. You can't just assume a practice is working everywhere. You have to verify it. You have to make sure you aren't just leaking nitrous oxide out the back door while you're putting carbon in the front.
So let's try to bring this all together for a final synthesis.
I think the main point is that we cannot simply return to the past. We have 8 billion and soon to be 10 billion people to feed. We can't feed them all with first-century technology. That's a fantasy.
But we also can't continue with 20th century technology. That system is clearly eating the planet and is becoming dangerously unstable.
No, the only path forward is to bridge the two. We need to merge biological domestication with digital globalization. The vision, I think, is a landscape that looks ancient. You see terraces, you see swales on contour, you see diverse crops, you see trees integrated with fields, but that landscape is managed with futuristic precision.
With satellite data, with genetic insights from the land races, with robotic labor.
A landscape that remembers its deep past in order to save our future.
That feels like the perfect place to leave it.
Hmm.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us in Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.